Yeah, so I'll briefly introduce you. So we have today Izabel Aguiar, right?
Yeah.
From Stanford University, who is going to tell us about cognitive social structures. She is neuroscientist, social network or neuroscientist? Which one do you prefer?
I like either. I think there's a little.
You're in like both worlds. I think in both.
Yeah, I want to be in both.
Yeah. I think that's a good strategy. Yeah, she studies social networks, and she's going to tell us about her research today. And by the way, she's in the job market, so take that into account. Consider that for any reference or whatnot. So thank you for being here, Izabel.
Thank you so much. Okay, so yes, thank you. My name is Izabel Aguiar. I'm a fifth-year PhD student in the Institute for Computational and Mathematical Engineering at Stanford, where I work with Johan Ugander. And today I'm going to talk about this recent project we just finished up on the latent cognitive structures of social networks. This is on arXiv, and I have a Git repo online as well. So the main takeaway of everything that I'm going to talk about in the next however long is that the non-negative Tucker decomposition offers new insights into cognitive social structures by identifying latent cognitive structure in people's perceptions of their network. And I'll spend the first part of this talk identifying and defining the background of these bolded words. So no worries if they're foreign. And then I'll spend the second talk applying this tool to a couple of different data sets as well. So I'll start off by talking about what a multilayer network is, because the tools that we'll use are more generally applicable to multilayer networks, and we'll just be applying them to cognitive social structures. So a multilayer network is if we have this group of people and we say, okay, these people are connected to one another, but we might want to be more specific about what connected to one another means. We might want to say, okay, who are your coworkers? Who are your friends? And who do you spend time with? And so we can take each of these different specifications of who are you connected to, and we can view them separately amongst the same node set. So in this case, we have these 5 people, and we can tell who their family members are, who their friends are, and who they spend time with. And if we view each of these as an individual social network with its own adjacency matrix, then we can stack all of these adjacency matrices up together, and we can view this as a multi-layer network now, where each layer of the network corresponds to a different way that things or nodes are related to one another. So in this example, the different ways that we can break up this connected to one another. Conveniently, we can also view this as a tensor, an adjacency tensor instead of an adjacency matrix. So then moving on, what is a cognitive social structure? Cognitive social structures are these fascinating things that were introduced by David Krackhart in 1987. And what they are is if we have a group of people that we're interested in studying the social network of, for each person in the network, we ask not only who are you connected to, but also who do you think everybody else is connected to? And we ask about these perceptions and connections, not just of one person in the network, but of every single person in the network. So eventually, we've asked every single person, who are you connected to? And also, who do you think everybody else is connected to? In doing so, we have as many different adjacency matrices as there are people in the network, where each different adjacency matrix corresponds to each person's perception of what they think the network structure looks like. So in all, we can view this cognitive social structure as a multi-layer network, where each individual's perception of the network corresponds to a different layer. So how do we understand them? There's been a huge amount of work on understanding cognitive social structures in different ways. And there's this original CSS paper from 1987. There's this wonderful review paper from 2013. And just an example of some of the more modern approaches towards understanding these objects is a latent space model for statistical analysis by Sosa and Rodriguez. In the original Krackhart 1987 paper, he proposes understanding these very rich data objects by kind of aggregating them or looking at them in individual slices. So instead of considering all of the networks kind of simultaneously, what if we just consider different single layer versions of them? So one way of doing that is looking at slices. So we can compare my perception of the network to your perception of the network, and that would be comparing 2 slices. We can consider these things called locally aggregated structures, which is either taking the intersection of all of the edges that were perceived, or just assuming that an edge between I and j exists if I perceived it as existing. And then we also have these consensus structures, wherein an edge between two people is kept in the consensus structure if some p proportion of people in the network also perceive it as existing. But the majority of CSS work has focused on identifying discrepancies between people's perceptions and some true social network. So either by comparing one person's perception to another, or comparing my perception to the aggregate, and kind of identifying these discrepancies. But what we propose to do is to use a generative model perspective of understanding these data objects as a whole, instead of identifying some true network that exists within them. To do so, we build upon a stochastic block model. And so to tiptoe our way into the stochastic block model for multi-layer networks, we'll start by just reviewing a single layer stochastic block model. So the single layer stochastic block model that I'll introduce and talk about here is specifically the one introduced by Balkar and Newman in 2011, wherein if we have a network represented by adjacency matrix A and a number of communities K that are latent in the network, the stochastic block model assumes that the ij entry of A is drawn from a Poisson process with mean given by this inner product. So specifically, we have an edge between nodes I and j, which can be described by i's soft membership to k different communities, j's soft membership to k different communities, and this thing called an affinity matrix, which describes the density of edges between each of the k groups. So kind of as an intuition, if we were only allowed to belong to one social group, not soft membership like it actually is, but just for intuition's sake, then if we have a math group, a reading group, and a soccer group, then to see the rate at which a soccer person interacts with a math person, we could look up that entry of that affinity matrix G. So moving forward into what we'll use as a stochastic block model for multi-layer networks, I'll introduce this tensor decomposition more generally. Called the non-negative Tucker decomposition. So the non-negative Tucker decomposition takes a tensor A, in this case an adjacency tensor, so it's n by n by L, but more specifically for cognitive social structures, this L is also going to be equal to n because we have n different perceptions. And we want to decompose it into an n by k non-negative matrix U, an n by k non-negative matrix V, a non-negative matrix Y, which is L by C, and then this thing called a core tensor, which is K by C. Now moving towards from this tensor decomposition to a specific model for a generative model for multi-layer networks, I'll stop calling it the non-negative Tucker decomposition and shorten it to the NNTuck. More details of this are also on archive, but when I say the NNTuck, I'm specifically referring to a particular generative process that we're assuming and a corresponding estimation algorithm that respects that generative process. So the NNTuck assumes that if we have an adjacency tensor A, a number of communities K, and now a number of layer communities C as well, then the AIJK entry is drawn from a Poisson distribution given by this slightly more complicated mean. So the edge between nodes I and J in layer K can be described by, again, I's soft membership to K different communities and J's soft membership to K different communities. Now we have this core tensor G, and then we also have this additional third factor matrix Y, which describes how layer K's affinity matrix can be written in terms of the core tensor. And we'll build up some more intuition about this in a second. But just as the single layer stochastic block model assumes that nodes belong to K outgoing and incoming communities, in hoping to describe a multi-layer stochastic block model that appropriately models the multi-layered aspects of this network, we also now assume that layers belong to layer-specific communities as well. So we can group together the nodes in communities and the layers in communities as well. And these layer communities are given in this third factor matrix Y. So to kind of build up what this means and how we can interpret this third factor matrix, we can go back to this multi-layer network that I introduced at the beginning. Who are your coworkers, who are your friends, and who do you spend time with? If we wanted to use what we know about a single layer stochastic block model to build a stochastic block model for this multi-layer network, one approach could be, we say, okay, your social membership is fixed across layers. What community you belong to doesn't change based on if you're a coworker, a friend, or someone who's being spent time with. And then we could go and we could build a stochastic block model for each layer. So we could find the affinity matrix for the coworkers layer, we could find an affinity matrix for the friends layer, and again for the spent time with layer. If we did that, there is a non-negative Tucker decomposition way of looking at this, wherein we stack those three affinity matrices together to be the core tensor. And in this visualization we see now, there's no third factor matrix describing the layer communities. We've just kept the node communities and then we've stacked all of the affinity matrices together.
So right now that means that you are treating them as independent.
Yes, exactly.
That's why, okay, yeah.
Exactly, yeah. But if we consider the actual questions behind this particular layer, this particular multi-layer network, as well as the color hints that I've given with green and yellow and blue, then it might be reasonable to ask, what if the layers are related to or dependent on one another in some way? So specifically, what if the generative process that describes who I spend time with is some sort of combination of the generative process of the people who are my friends and the people who are my coworkers? So mathematically, what if that affinity matrix for the spend time with layer is some linear combination of the affinity matrices for the friends and the coworkers layer? If this is the case, if there is this type of layer interdependence in a multi-layer network, if this third affinity matrix in this case can be rewritten in terms of the first two, then we can capture that dependence in this third factor matrix. So now instead of the third factor matrix being the identity, saying that all of them are independent, we now see that the core tensor has deflated to just the two affinity matrices that we care most about. And then the third and the relationship between the third and the first two is captured in that third row of that third factor matrix. So this is the tool set that we're going to use to understand cognitive social structures in a particular way. But what does the non-negative Tucker decomposition of a cognitive social structure mean? So before, if we had a multi-layer network that we were decomposing into latent social spaces and a latent layer space, we now view the cognitive social structure as a multi-layer network, then the layers correspond to people's perceptions of the network. And so what we're identifying in that third factor matrix is a latent cognitive space. So what does this mean and how can we interpret this? So if people belong to these three groups that I referred to before, like a math club, a reading club, and a soccer club, then that could be expressed in this latent social spaces. But if we also say that people view their perceptions of their network, if they rely on certain rules to recall their networks in particular ways, so some people have a blue set of rules for recalling their network, and some people have a yellow set of rules for recalling their network, then this can be captured as well. So the social factor matrix will group together the people based on others in the network structure. And so this is the latent social space that's usually uncovered with stochastic block models. But the cognitive factor matrix groups together people with others who perceive the network similarly. There's a really nice interpretation of this cognitive factor matrix through established social theory. So in particular, Baldwin's 1992 theory of relational schema, which I'm quoting from that review paper in 2013, is that the observation that individuals' recollections of social interactions exaggerate systemic structure provides an important insight into the cognitive processes that underlie network perceptions. Namely, it suggests that individuals rely on schemas to organize and remember their surrounding social networks. And relational schemas frame our experience of the social world. They describe expectations about the nature of relationships between people, defining what aspects of social interactions individuals will pay attention to, as well as the attributes of others that are meaningful within those interactions. This is further explored in Judith Howard's 1994 theory of social cognition, wherein she says that social cognition articulates explicitly how social structures are carried in individuals' mental systems. The content of the group dimensions on which people are prone to categorize reveals the connections between cognitive and social structures. So relational schema describe the generalizations or the patterns that we rely on when we're recalling or making social connections. And social cognition tells us how these structures are perceived and carried in our minds. In the data collection of cognitive social structures, we're asking every single person in a network to say what they think the network looks like, to recall who they think is connected to him. And there's been a lot of research on people using different compression heuristics to recall and store large networks. So for example, in this Brashier's paper in 2013, they found that people necessarily rely on some sort of compression heuristic or schema or rule to carry large networks in their minds. In this Kilduff et al. Paper, they found that people take small world shortcuts to recall their networks. So they're better at recalling things if they assume that there's like some small world attribute to it. And even in 1992, Freeman said that people exaggerate the structure present in their experience in order to build a simplified cognitive conception. So then this gives us some more kind of like power behind this cognitive factor matrix as grouping together people who think similarly to one another, because we can think of it as identifying people with a shared relational schema. So then again, this Y factor matrix can identify people who have these shared relational schema. And in this way, it's also an operationalization of Judith Howard's theory of social cognition. So the last thing I'll introduce before we go into some data sets is just different types of structure that we can assume using the non-negative Tucker decomposition and how it relates to different assumptions in the relational schema present in a network. So one of them is a cognitively independent non-negative Tucker decomposition, wherein we say that everybody has a unique relational schema. One person's relational schema cannot be described by a linear combination of any of the other people's relational schema. In this case, that third factor matrix is the identity and must be the identity. Another one is a cognitively dependent non-negative Tucker decomposition. This is like what we introduced earlier, where in this case, there are two people who have relational schema within which everybody else's relational schema can be considered alongside. So maybe one person really, really thinks that this one rule is true about how people interact with each other, and one person thinks this opposite rule is, and then everybody else is kind of like a mixture of those. And then we also have a cognitively redundant non-negative Tucker decomposition, wherein everybody's relying on the same set of rules to recall their network, the same generative process. I won't talk about it much today, but it's something that's super interesting that I've enjoyed thinking about is this last assumption of social cognitive agreement, wherein we say, okay, your social group is also exactly the same as your cognitive group. So the people you're hanging out with and forming social connections with, they're informing the relational schema that you use. So in this case, all of the math people have the same relational schema when they're recalling their networks. Okay, that was so much. We talked about all of these things. Before I move forward into applying these tools to a couple different data sets, are there any questions or clarifications?
Yes, one thing that's not entirely clear to me is the Y matrix.
Yeah.
So that's the latent cognitive social structures, right? So
latent cognitive space, yeah.
Yeah. But it is the way that you were posing it before is like if you have, say, 4 layers in a multi-layer network, then you essentially would take one of them and here there's a composition of the three other of them? Or is that how you
Yeah, so tensors like blow my mind. I know I'm not using the right vocabulary when I describe this, but the way that I've been able to explain it to myself is that just as in like a matrix that has linearly dependent columns, we can rewrite it as just like a basis and we say like, okay, the fourth column is just a linear combination of the first two columns.
Okay.
The same way is thinking about the linear dependence of these affinity matrices in the generative process. So, and specifically like, just as we would write like, oh, like the fourth column is like alpha 1 plus beta 2, we can put those alpha and beta in this non-negative Tucker decomposition into that third factor matrix. So that's like the linear algebra behind it, is that like there's some sort of linear interdependence between the affinity matrices of the different layers, but more like contextually maybe is that like if my generative, or more generally for multilayer networks, like oftentimes multilayer networks can take on the form of like, okay, like who do you ask to babysit your kids? Who did you call today? Like who would you borrow rice from? And if the generative process for each of those networks is the same or very similar, then it's kind of redundant to like include the affinity matrix for each of them by saying like, okay, like math people interact with book people in this way. Oh, and then they interact with that way in that layer as well. Oh, and then it's the same for that layer as well. Or like, oh, it's a combination or a mixture of those two. Then that mixture is then like captured in that third factor matrix. So that it's more helpful with visuals, at least for me. So yeah, I think this example really helps me because specifically the wording of these questions is like, okay, like the people I spend time with just realistically are my friends and are my coworkers. So I don't need to have like a whole other generative process describing who I'm spending time with when I already have generative processes describing who I'm friends with and who I'm coworkers with. And so that like dependence is captured in that third factor matrix. Right. Yeah. And then in the sense of perceptions, our generative processes are like accounting for what rules we're using when we recall these networks, because these are all just perceptions, right? So it's not like there's some ground truth of like, you know, you like got it right that these two people interact, so like good on you. It's like, well, like I don't actually know if those two people interact, but like they work in HR and like they work in like humanities, so like maybe they interact, and like that's my set of rules for like recalling this. Right. Yeah.
I mean, it doesn't matter in terms of which in which layer do you take as the so
yeah,
the composition. Yeah, you just.
That's an excellent question. Excellent question.
You can take any layer and use it as a reference, same question, or.
So I have like some backup slides that talk about this, but it's actually like a very interesting question. So when we estimate the non-negative Tucker decomposition, the estimation technique that we're using for this, it's a non-convex optimization problem. The estimation technique that we're using doesn't specify like, okay, I'm going to find your affinity matrix and then I'm going to find mine and then everybody else's will be written in terms of that. It just that you specify like, okay, I want two layers or two affinity matrices, and then find them. But you can, just as you can kind of rewrite a matrix in like the basis of two columns, you can rewrite them in the basis of two people in this case. So we'll actually look at that. And yeah, great, great point.
Thank you for your patience.
Oh no, I love talking about this. It's so confusing to me, which makes it even more fun to try and figure out. The first data set that we'll look at is Krackart's 1987 Advice Cognitive Social Structures data set. So in this network, there was a group of 21 managers in a high-tech firm, and each of them had different hierarchy. There was a president, there were vice presidents, and there were supervisors. And David Krackkart went in and he said, okay, every single person in this network, tell me who you think goes to whom for work-related advice. So if you have a question about work, who are you going to and who do you think everybody else is going to? And what we're visualizing here is the intersection locally aggregated structure. So we're keeping an edge if anybody perceives it as existing. And this is a whole other wormhole that I could get into, but the approach that we use to find these hyperparameters K and C, so C being how many affinity matrices do we want to look for that we're like considering everybody else's affinity matrix with respect to, and then also how many social groups are there. The approach that we're using to determine these hyperparameters is using a 5-fold cross-validation link prediction task. So what we'll see on this plot is assuming a cognitively independent assumption will be with this black line, assuming some sort of cognitive dependence with C varying based on the color, and then a cognitively redundant assumption. So this is assuming that everybody's sharing the exact same relational schema. So in doing so, we see that the cognitively independent performs just as well for most values of K. Cognitively dependent kind of varies depending on K, but cognitively redundant assumption always performs worse. Kind of squinting a little bit and weighing the different parameter values in this case, we decide to look into the non-negative Tucker decomposition that's identified when we assume the K equals 3 and C equals 3 as well. So that's assuming that there are 3 cognitive groups and 3 social groups. So in doing so, we can view each person's proportional membership to each of these social groups, as well as to each of these cognitive groups. So in the example I've been giving for social groups, I've said like, okay, you're either a reader or you're a math person or you're a soccer person. But in these models, there's actually a soft membership flexibility. So you can be like 30% a reader, 40% a mathematician, and however percent a football player. So we'll view each different coloring as each person's proportion to each social group. So the social groups that are identified in this particular estimation largely correspond to different departmental affiliations, barring a couple things. So we see that the first social group mostly groups together those people who are in the left department, and the second group mostly the people who are in that bottom department, and the third social group mostly the people on the right. The exceptions to this are that that department that's in the upper center, who are like mostly spread across all 3 social groups, as well as person 6, who's the president of the company, who's also equally spread across all of these social groups. So at least for the president, we can be like, yeah, that makes sense. Like you don't belong to a department. I don't have enough information about what each of these departments actually were, but it's interesting to see that that 4th department is equally spread amongst all of the social groups. The cognitive space, however, isn't as easily kind of identifiable according to these departmental affiliations or according to any of the other metadata I have, which is tenure, age, and reporting status. So what we can do to kind of interpret this cognitive space a little bit more is exactly what you were just asking about, which is we can take the core tensor and that cognitive factor matrix and rewrite it all in terms of 3 people's affinity matrices. So in terms of 3 people's identified relational schema that they're using. There's some linear algebra behind the scenes as to what 3 people we're choosing. But in this case, the 3 people that are identified are person 6, person 14, and person 10. So we can rewrite this all so that like the first network we see on the left, person 6 belongs entirely to that group and not at all to the other groups. And everybody's proportional membership reflects how similarly they perceive their networks to him. The second one similarly, but for person 14, and then for the last one for person 10. So person 10 is mostly interchangeable with actually a lot of other people. He doesn't represent that relational schema more so than these other people in the network, particularly 9, 18, 15, and 7. And he seems to represent the cognitions of everyone other than person 6 and person 14. Person 6 is the president of the company, and so the people who have a shared relational schema with person 6 are viewing their advice network similarly to that of the president. But person 14 is a little bit more elusive as to who he is or why he might be capturing some sort of different relational schema than the other two groups. Until, yeah.
Yes, when you say they're viewing similarly to the president, you're talking about the whole CSS, right? So not just my local friends with,
Exactly.
but rather who do I think everybody seeks advice?
Exactly.
They have a shared, okay.
And not even like I think more traditionally, like the way that we say that people view the network similarly is by actually like comparing those slices and being like, okay, person 6's perception, how similar is that to person 5 and person 16? But now instead of saying like how similar is it edge by edge, it's how similar is it in terms of the generative process. Right. So the rules that they're relying on. Yeah. Right.
So they may have a very different CSS network itself.
Exactly, but it's relying on the same rule.
The thing that generated it's similar.
Yes, yeah. Exactly. So this person 14, I was like, what's so special about him? Until you look into the original Crackhart paper and you find this wonderful quote. So he says his own perception is that he's very active in the network. Advice is sought from him by 12 people. He actively seeks advice from 20 others, which is everybody else in the network. And he's on the crossroads of this network as evidenced by his high betweenness score. But this self-evaluation is not shared by his coworkers. Only 3 of his in degrees are confirmed, and only 9 of his out degrees are confirmed. And his betweenness in this locally aggregated structure just about disappears. The consensus structure reveals that people generally think that nobody approaches him for advice, and if he only goes to 5 other people for advice, and he's not in between any other pair of people. So we now see that this person 14 kind of represents a person who was either very overly optimistic about the advice network, or was just a very noisy realization and like didn't try at all to actually like say who was connected to whom, but just kind of was like, whatever, I'll choose everybody. But either way, he's identified as having a very distinctly different relational schema from everybody else in the network.
So in the paper that we are writing, yeah. I think we have an outlier, and I think that might be the same person. We have it on the test, and it's like, okay, no, so this is something odd about, okay, so I think it might be the same person.
That's awesome. That's so fun. Yeah, I bet. Okay, so the next data set I'll talk about was this one that I was very excited to find. It's from 2019 from Keith Hunter. He collected it on a classroom of 20 students who traveled to the Bay Area for a summer leadership course that was 6 weeks long. He collected the cognitive social structures for the advice network and the friendship network every week for each 6 weeks. So we actually have a longitudinal cognitive social structure data set for how different perceptions changed over time as well. For this particular setting, I'm only going to consider the first and the last weeks of the friendship network, but just keep in mind that a lot more exist as well, and they are available. So again, we'll do this cross-validation to choose our model specifications, and specifically for this first week, we'll consider the NNTuck with C equals 3 and K equals 2, so 3 cognitive groups and 2 social groups. And again, we'll view each student's proportional membership to each of these groups. So we see that the first social group and the second social group are kind of organized like this. We'll interpret it in a second. And the cognitive space mostly organizes people according to their social group, with the exception of this third cognitive group, which kind of has these people 3, 6, and 13 and 15 a little bit too, as belonging to their own cognitive group. So one wonderful thing we know about this data set is we have access to each student's self-identified gender. There were only 2 self-identified genders in this case. We have their self-identified race. We have their undergraduate institution that they were traveling from. We have their major declaration. And then there are also some other cool and weird things, like each student had a roommate in the social network as well, that they lived with for the whole 6 weeks. Also, there were 4 different study groups that each student had to do all of their classroom activities with. But particularly, if we look at gender compared to these identified groups, we see that the social spaces are largely corresponding to the self-identified gender of each of the students. And the cognitive space, again, barring these people 3, 6, and 13, and 15, also corresponds to these gender lines. So people share a relational schema according to people who have the same gender identifier as them, except for persons 3 and 6, who actually have different gender identifiers, but show up in this different cognitive group. Turning instead to look at the last week of this data set, we again look at the specification of 3 cognitive groups and 2 social groups. But now we see that the social groups are no longer well explained by those gender lines. And actually looking at all of the other metadata we have access to, they're not according to any of those other easy identifiers. They're not according to your race, they're not according to your major, they're not according to who you live with. They seem to be more complicated than that. And again, the cognitive space also reflects this difference, where no longer are you sharing a relational schema with others with your self-identified gender or race or other identifiers. This has a nice relationship back to Judith Howard's theory of social cognition. She says in that same paper that gender and race are social systems of differentiation that are especially prone to cognitive categorization. And even that we see these in the first week, but not in the last week, can be well explained by her theory. She says systems of classification must be relatively simple in order to provide a beginning place for interaction. This interactional requirement generalizes the principle of cognitive efficiency. Interaction is easier if there are fewer cognitive distinctions to consider. The constant use and interaction of dichotomies such as gender may help to keep them simple. So her theory of social cognition can even explain that we see that in the first week, students are relying on these like easy rules according to their gender to recall their network, which becomes a lot more complicated by the last week. And even then, she says, if schemas are to be sustained and reproduced over time, they must be validated by the accumulation of resources that their enactment engenders. Schemas and resources constitute structure only when they imply and sustain each other over time. So seeing that these relational schema weren't engendered throughout the course, that you couldn't just rely on your self-identified gender for your relational schema, but that you had to form more complicated nuances of who was friends with whom and new rules, was in some ways like an applause to the course, right? Like we can imagine some courses or some environments where these easy systems of cognitive categorization could be just reinforced and engendered, and they might not change over time. So broad takeaways, we viewed the cognitive social structure as a multi-layer social network that identifies different perceptions of a social network. The tool we proposed using the non-negative Tuck decomposition operationalizes Judith Howard's 1994 theory of social cognition by identifying cognitive structure or different relational schema in perceptions of the network. And we find low-dimensional structure in the cognitive space of the advice network from Crackhart's 1987 study. And in exploring Hunter's 2019 longitudinal friendship CSS, we find an adaptation in relational schema over time, away from cognitive categorization determined by gender. Part of the most exciting part of this project for me has been thinking up new and fun questions, which I could spend another hour talking about. Just to go into them a little bit, identifying different social spaces is one way that we've identified different seeding strategies if we want to like seed some gossip in a network or seed some information about vaccinations, is by seeding one person in each social group. But we share information not according to some true network, but according to what we think the network looks like. So are there ways that we can evaluate different seeding strategies according to different cognitive group seeding instead of social group if they aren't the same. The non-negative Tuck decomposition distinguished differences in cognition and differences in correctness or noise. So like I said, we identified that person 14 as being different from the rest, but is that because he had some like very different rules for recalling his network, or because he was just like a noisy realization and like didn't care about it? If it is noise, are there like other settings in which we could use this tool to isolate this noise? And then finally, these CSS data sets are kind of hard to come by because they're like massively hard to do. And so are there like perception data or other ways that we can infer people's perceptions and different cognitive rules kind of like in the wild? Like, are there other like existing data sets that might have perception data kind of hidden in them that we could just kind of tilt our heads at to get a grasp of? That is all I have to talk about, and I'm happy to take any questions, and thank you so much.
Very, very interesting. I do have a few questions I think I'd like to discuss, but if anyone wants to answer, should first, or no, from the chat. Well, let me start. I think this is great. So as now I was telling Izabel that I also do CSS. I'm actually like working on a paper that we're resubmitted now to social networks about CSS. And maybe the individual 14 is the same that is causing some issues with that for us, for some hypothesis testing. I had to check the data with my colleague about it. But one thing that it made me think about is actually there are three things that I'm not sure if you have seen, but I'm pretty sure that they might come up during our review in social networks.
Sweet. Yeah, thanks.
So first of all, this can be related somewhat to multi-layer exponential random graph models.
Yes.
So there is so you know, in ergoms I talked about this group in the past. In ergoms we use ergoms to understand the rules that yield the structure that we observe in the graph. And this is very much related. In the case of multi-layer networks, we do have multi-layer ergoms, in which you could, for example, do some hypothesis testing regarding how the way in which these layers are interrelated. So not just within. So I'm pretty sure. I'm not entirely sure how this can be used with CSS, but I think that a reviewer may like think about this while reading your paper. I think it's super related. And the other thing that I was thinking about, let me see, I wrote it down. Oh, and again, by the way, I'm an ergoms person, so that's why I'm trying to connect this up with ergoms. There is literature in network, a type of model that's called latent ERGMs, in which they try to do exactly something like this, right? So you say that you observe a graph, but this network, it was originated based on a latent structure that we, for example, of shared perception or knowledge or something like that. And that and latent space ergoms try to do exactly that. So you can identify, like you are doing, you can specify how many social spaces there might be, and based on that, it will place nodes on this latent social space to see how it's related to the perceived graph.
Yeah, it'd be interesting to see how different viewing spaces identified in different types of methods, like an ergom or an SVM, would identify different things.
Yeah, no, so that's but I think that ultimately all of these things might be somewhat. There might be a way to like map these methods in between. I think there might must be something that's really cool. Yeah, and the other thing that I was thinking of, let me see. Yeah, so so you show us that you were using AUCs for calibrating the model, but as a statistician, I will think about doing some hypothesis testing instead. Yeah. And I see that you have likelihood ratio tests, and I'm thinking that may be what you're thinking about. Yeah. So if you can talk a little bit about that.
For sure. Yeah, let me find the right slide. Yeah, so another whole thing that we did in both the first paper, like establishing this model as well as extending it to different cases in this work, is using a likelihood ratio test. to test between different model specifications. So the helpful thing is that each of these different NNTuck specifications are actually all nested within the layer independent non-negative tuck decomposition. So the way that we can kind of see that is that each of these so the model we're seeing on the right, which is like the layer dependent one, is exactly the same as the one that's written on the left. And the one that's written on the left kind of implicitly has an identity matrix in that third factor matrix position. So kind of by like doing the tensor multiplication of the core factor tensor by that Y factor matrix, we can always rewrite these in terms of a layer independent non-negative tuck decomposition. Oh, I had a slide, I didn't even have to say it. Yeah, so we can always rewrite these models in this like larger model. And so that gives us like a great way to approach this using a likelihood ratio test, by comparing these hypotheses of, was this multi-layer network that we're observing drawn from a redundant or an independent or a dependent or an independent with this number of degrees of freedom. Right. So we have all of these different definitions for different layer dependence tests. This is great. And in an application, like all of the observations that we've made from the likelihood ratio test have corresponded to using this test AUC. There are some like, and this is getting so like hyper like focused on this one technical question that I've been a little obsessed with, which is latent space models don't satisfy the conditions of Wilks' theorem upon which the likelihood ratio test relies. Specifically because we can kind of always shift things around and rewrite models in the same way, so they're not unique. And so, and moreover, and more importantly, actually, is this is a non-convex optimization problem that we're like estimating using lots of different random initializations and like taking the highest log likelihood out of like 50, for example. And so another specification of Wilks' theorem is that you must be at the unique highest likelihood model. So to approach this, and I don't have a slide on this, to approach this, we've actually used a more modern likelihood ratio test. It's called universal inference, and it's the split likelihood ratio test. It's like a 2020 Wasserman paper, which doesn't necessitate any of these harder conditions, but it is a lot more conservative. And so, and then there's a whole other thing with when you want to test for social cognitive agreement instead, you kind of have to change your algorithm. It gets a lot more complicated. But all to say, yeah, we have developed these tests to kind of like validate or compare the conclusions we might draw. I feel a little bit like I would like to pursue the technical questions behind them more before I just rely on them as being used. Yeah. But yeah, there are lots of ways to choose.
No, this is great. Well, a dirty way of doing some hypothesis testing without relying on all of this could be actually taking your AUCs and sampling from the what kind of, I don't want to say positive distribution because it's not a positive distribution, but in principle, you can generate confidence intervals for AUCs. And that way you can go ahead and compare whether you have a significant improvement in your observed AUC or whatnot. And another thing I wanted to comment out is that you need to consider AUCs are not very good when you have unbalanced data. So if your network is too dense or too sparse, AUC will be a little bit tricky. So instead of that, I suggest using mean absolute errors. And if you're using mean absolute errors, then you can I can share with you, but there's a way of actually doing hypothesis testing with mean absolute errors, because you can treat them as like by Bernoulli random variables, and you can have like a null distribution based on that and have an exact test that I can share with you about later.
Okay, yeah.
And one last thing that I remember, that because you said you are using the locally aggregated structures, which rule are you using for that? Because I remember, if I remember correctly, so you have like a few rules. Blacker has like a one intersection, additional or something like that. I don't remember.
Yeah.
So which rule are you using to reconstruct the social network?
So I'm not using any of them.
Okay.
To visualize them on like the slides, I'm using an intersection. But in all, we're just considering this as like the whole three-dimensional tensor. So not doing any aggregation.
Perfect. Okay, now I get it.
Yeah.
Now I get it. Now I
Yeah.
get it. Okay, because of okay, that makes sense. Yeah. So then what I was about to say doesn't it's not relevant because there's a way for aggregating cognitive social structures that it's recent and again, so it's showed up in social networks. That's called the BNAM method. I think it's something like Bayesian network aggregated model.
Cool.
Something like that. Because yeah, so Crockett's rules are like very simple, like intersection, additions, but then there's a more sophisticated method that in which you can use prior information to improve the accuracy of these things.
Yeah. Yeah, a lot of them were like recent latent space or like other methods that I found in my lit review for this. Were like focused on some sort of like better reconstruction of the real network. So if this true network of like taking everybody's ground truth as ground truth, or like, okay, 50% of people agree it exists, then that's the ground truth. Then people had come up with these like more sophisticated ways of doing that. But they still were focused on this like, okay, what's the true network and how does this compare to the true network? Which I think almost like philosophically like denies this interesting question of like, okay, what if they're all true? Because like they're each true to each individual. And what are we missing out on by like assuming that there is some sort of ground truth?
So individual 14 lives in the like the center of it.
Also, relationship is dynamic, right? So
exactly,
right in this moment is true, not the next minute. So there's no ground truth.
Exactly.
I don't know.
No, and that's why the last example was awesome, in which you have like the switching. Now afterward, like gender and race was not explaining the data, which means that ultimately they found another feature, maybe some other characteristic or something else that like binds them together. Or something. I don't know.
Yeah.
And also we collect all the data by asking people how you feel, right? And then maybe some like social desirability issue. People didn't want to. So
data might be biased, and as Izabel says, so you also have like a recollection issues, right? So it's not 0-1, it's more like I think that they're friends, like 50%.
Especially with something like, well, not especially, but like in like a work situation where it's like who goes to who for like work advice, and it's like maybe like that really is just like what rules you're using. Like, okay, like everybody in this department goes to each other, like obviously, or like, you know, like you're necessarily relying on some sort of set of rules instead of like, oh, I know for a fact that you go to him for advice. That's a different thing to have an understanding.
Okay. Well, it's a great talk again, and thank you very much.
Thank you so much. Thank you for that.
Stop recording now.